And then after CodeCamp, people are like, oh, these slides are cool. What'd you use? And people say, oh, you should do a talk on Manim. So it's like, here's the talk. So here are some links. All the content here is on GitHub, Manim talk, that subdirectory. I have a Blue Sky social link and my email address. And all these slides are live if you want to follow along. All right, so who am I? So I'm Nathan. I'm the founder of Shimmer Math Labs, which is my money-losing garage startup that has no sales. Yes. Previously, I worked at places like NVIDIA, Qualcomm, and Amazon Lab 126. And so basically what I do is I program math. So I do a lot of high-performance programming, a lot of weird math stuff, AI-related at NVIDIA, lots of, different precisions, stuff like that. So I like math, I like programming, I like both together. I'm currently working on synthesizer algorithms and audio deep learning. So this is things like text-to-speech, lip sync, generating weird sounds from textual descriptions, things like that. All right, so why Manim? What does it even stand for? So it stands for Mathematical Animation Engine. And this is sort of an example diagram or graph you could make with Manim. The way I see it, Manim is really about effective communication. Like it's about technical topics, and it comes from math, but I think it's actually a little bit more widely applicable than just math. Technical topics are complicated, and they're hard to describe perfectly. And so here's my little explanation of like least effective way to describe complicated topics to the more effective ways. So least effective is pure text, just reading descriptions or talking. Then having one complicated diagram, that's a lot better. You can see it and see the organization. Then having a sequence of diagrams to show what's changing is a little bit better. Then animation, showing things actually changing to describe what's going on. And then the best is interactive animation. So things like demos where you slide things around and you can see them changing in real time. That's the most effective way to see what's going on. And Manim can do all these different levels, but really it focuses on the animation side. That's what its strength is. The other side is actually getting it right. So if you sit down at pen and paper and draw something, you can get things right, but it actually takes quite a bit of effort to make sure everything exactly lines up. And if you like plot a function, it takes quite a bit of work to make sure the function looks correct. And so as programmers, we like things to actually be correct, so you can use real data and not just fake data. You can have version control, and so you can fix the problems and redo the graphs and the animations over and over again until it's exactly right. And we're programmers, we're coders, we got to code. This is the way to do it. So Manim was created by Grant Sanderson. He's the creator of 3 Blue, 1 Brown YouTube channel. And he also won the American Mathematical Society Communications Award in 2023 for mathematical communication. So like one of the top mathematical communicators in the world has created the software, and it's pretty popular. It's used by a lot of YouTube channels, and it's becoming more and more important for talks about very advanced AI math stuff. Tend to use more and more animations now because it gets very dense. And so this is becoming more important in mathematics, I would say. So part of the history, around 2019, this is kind of what the 3 Blue, 1 Brown videos look like. This is calculus. So there's a lot of equations. There's functions showing something. There's lines and tangents and annotations. And I'm not showing the actual animation here, but this line is moving, the dt and the ds are changing. That's kind of the idea. That was the 2019 kind of era. More recent one in 2025 is a video about large language models explained briefly. So here you can see there's an example text on the top with the words, and each word has an embedding, which is a column vector. And then things are happening in the LLM, and it's making predictions, which will end up on the next token on the right. So this is a video explaining how LLMs work with examples that have real numbers. So these are not, they're sort of fake, but they're not entirely fake. There's actually an LLM running, generating the numbers, and so you're seeing what's happening in a small toy model, which is pretty exciting. So history of Manim as a project. Originally, it was just the code that Grant used for his channel. Then it was open sourced, released with an MIT license. Hooray. Then the community, like many different developers, forked the sort of personal repository of Grant and made it into a big open source project. And so that's the community edition. That was in 2020 until the present. And it's manim.community, pretty easy to find. And the caveat here is you have to be a little bit careful, because if you watch the videos on YouTube, he's using his original fork. And if you look on Stack Overflow, many of the responders are confused about versions. And if you ask an LLM to code for you, it will almost surely be confused about versions and not understand the differences unless you are very careful about prompting it. So be careful about this edition stuff. It's not a huge difference, but it will make your code not work. And new projects should always use the community edition. The only reason to use the original fork is if you want to follow along to a specific video. All right, so installation. How do you get Manim? So on Linux, here are the steps. The main complication is that you do have some dependencies before you can just install it in Python. So this first line, there's a sudo apt install line. There's a bunch of things that I already had on my system, but not every system has them. And so you need these. Then the recommended way I would recommend to install Manim is using UV, which is the latest Python package manager tool. So UV is a Rust project for doing binary dependency management for Python. And it can actually install Python, build Python packages, install binaries that Python needs very quickly. So UV is definitely the way to go. So this is how you install UV. Then you start a new project with UV in it. It creates a directory for you, and you just do UV add manim, and it should work. And here's some links. This is links about installing UV if you have trouble there. And Community Edition has a bunch of UV-specific installation instructions for how to install Manim using UV. There's a whole bunch of other ways too, like Docker containers and using pip and all these other ways. But this is my recommendation, use UV. So UV can be installed system-wide or per user. Typically, people install UV system-wide. Then once you use UV, it has a cache that's system-wide, but it will install the links to the cache per directory. So the cache of the binary things it downloads will be shared to save for efficiency, but it acts as if every directory has its own Python version, its own libraries, its own dependencies. Yes, yeah. It's UV is the new superpower venv. So here's for Windows. This is using PowerShell. To install UV, you have to do this command, which I don't fully understand. I think you're allowing things you're not supposed to allow. I don't really know. Then once you have PowerShell installed UV, then you can install Python using UV. And this is necessary in Windows because Windows may have Python already installed going to the store, and so you have to use the UV Python install. Then after that, it's pretty much the same. One caveat is you do have to have FFmpeg installed, which can't be installed by UV. And in Windows, you have to go to a download page. If you have a better way to do this, let me know. And if you want to do math formulas, rendering math text, you also need mictech. And so that's a mictech.org download. Mac is pretty easy. Install UV, and it should just work. I don't have a Mac to test. That's why this slide is simpler. All right, so here's the basics. Manim is a Python package, but it's also a command line, which is a little bit confusing. But here's how you use it as a Python package in your Python code. So you do from manim import star, then you define a class that descends from scene, and in that class you define a constructor or a method construct that takes a self, and then that's where you write your code. So to render this scene, you're going to call the command line and tell it, make a create circle scene. And to do that, it will construct it, follow all these things, and then it will have the scene and it will render it. This is kind of the idea. And the manim import star is not standard Python best practices, but it is best practices for manim. And it's probably a whole essay about why that is, but that is the standard practice for manim code, I would say. So if you see this code, you can probably guess what it does. It creates a circle by calling circle, its constructor. Then it sets some parameters of the circle, set the fill to pink with an opacity of 0.5. And then self, which is the scene, will create the circle. And so this create will take the object and turn it into an animation, and then play will play the animation. And so if we save this into example.py, we can then render that scene. So here's how you render it. It's manim render -pql example.py create circle. So we're using the command line. We're giving it the file name here, and we're saying -pql, that's preview quality low. And then that command will create this MP4 file down here. So it'll create media, videos, example. For low quality, it'll be 480p, 15 FPS, create circle.mp4. And this is what it looks like. Amazing, it created a circle. And you can see it was actually sort of animated, right? Drawing the circle. Yeah, there's one pixel missing, and in low resolution, it's actually kind of visible. Let's see. Yeah, so here's some command line options. So the P is the preview, QL is low quality. Here are the different quality levels. Yeah, the frame rate is actually more important to my eye than the resolution. But so here's a QP quality demo. So 1440, 60 frames a second. I don't know if you could tell if it was smoother or not. This projector may or may not be 60 frames a second. Yeah, and in general, low is very fast to render, like much faster than the high quality ones. And it's good for development, like when you're placing things around so you can see what's going on. Medium is maybe okay for slides, like from projectors that can't really do fast rendering. And then high, or even better, is better for YouTube. So it's a Python package, Manim's a command line tool. You define classes that descend from scene. You can have more than one scene per file. And then you render the scenes by calling the command line tool. That's kind of the idea. And then once you have the MP4 files, you can edit them into bigger videos. You can put them in slides, whatever you want. All right, so now I'm going to go through a few different examples showing more and more complexity of Manim commands. So please stop me if something doesn't make sense. So here is drawing two things next to each other. And this one's a little bit tricky because it actually doesn't generate an animation, it generates a static scene. So two objects, square equals square, set it to blue with full opacity, create a circle, set the circle to be pink with full opacity, move the square next to the circle on the right. That's how to interpret that. And then to the scene that we're in, add the square and add the circle. And the tricky bit here is that it's a static image, right? So this next to moves the location directly. It doesn't create an animation, it just moves it. And this add adds it to the scene, not as an animation, just adding it directly. And so the output is actually a PNG file, not an animation. You can see the square is to the right of the circle. All right, so now let's try and make it an animation. So now this time we have a square equals square, set it to red, create a circle, set it to yellow, move the square next to the circle onto the right, add the square, wait, add the circle, and wait. And so add adds the object directly, and the wait will pause for 1 second. And so now we start out with the square already there. If I play it, the circle pops into existence after 1 second and then stays 1 second. Is this making a little bit of sense? No sense? I feel like people are getting it some sense. So no. So the circle is a radius 1 circle by default, and you can change it, and it's always at the origin by default. And so the only reason these are not overlapping on top of each other is because I moved one of them. So in this case, I moved the square I moved next to the circle on the right. So this next to actually calculates the bounding box of an object, and then here, because I put it on the right, it goes to the right, adds a little bit of buffer, and then that's where it will move the square. Yeah, you'd have to make a smaller radius, to say where to put them. Yeah, exactly. Yes, you could. You definitely could. All right, so that popping into existence is kind of not very nice. And so there's actually a better way to animate things, and that's the create animation. So create just takes an object and, does some looking through the vertices and drawing them one by one to sort of smoothly cause them to be drawn on the screen rather than just pop into existence. It doesn't always look great, but it looks better than just popping. So here's an example where there's a square, a circle, we move the square next to the circle, then we animate the square being created, wait a second, animate the circle being created. And now you can see there's nothing to start with. Draw the square, draw the circle. And the exact order of vertices that it draws sort of depends on the internals of Manim, so you shouldn't depend on that. It's just a way to have things smoothly come into existence. Yeah, so this one starts on the rightmost and goes counterclockwise. Let's see. I think it's the same. Yeah. I already did that one. All right, so now, as we said, this is Python. We don't have to keep doing line by line, do everything ourselves. We can have Python code do this. So now let's do 3 squares by using a for loop. So here, for I in range 3, create a square, shift it to the right based on this I index, so they'll be in different positions. Then create the square and wait. And this right and left are vectors that you can add to move things around. And so this shift moves from the origin to an exact position you're specifying. Yeah, don't ask why I did right and left. It doesn't make any sense. So you can see there is drawing the square, waiting 1 second in a loop 3 times. All right, so there's more ways to place objects. This is showing some other things. So this is move to, just gives a specific place to move. Next to moves relative to an existing object. And align to looks at the bounding boxes and can align left, top, down, right. And so in this case, we're aligning a circle left side to the left side of the triangle. So we're creating a circle, square, and triangle. We're moving the circle left 2, moving the square to the left of the circle, then aligning the triangle left side to the circle left side, and then adding everything to the scene. So that's what it looks like. These left edges are aligned because the leftmost point of the triangle, leftmost point of the circle are lined up. And then the circle is to the right of the square. I think that was the logic. All right, the next thing is we want to animate things beyond just like being created, being drawn. So here is shifting things as an animation. So here we create a square, we shift it to the right 2, and this shift won't be animated, it'll just move it before anything is even drawn. Then we'll play that create, so this will show that square being created. Then we'll play an animation of a shift left by 2. So animate is a whole library of methods that look like the root methods, but they're actually, they create animations instead of just doing it immediately. So animate shift will return an animation that moves the object left 2. So we're starting out by starting right 2, and it will animate to the left. So it was created and then slid left. So next thing is, what about groups? How do we organize things to be more and more complicated? So here is a square and a circle. Move the square to the right of the circle. Now we create a group, and I'm using vgroup here. So vgroup means groups of vector objects, so we can apply different transformations to them. We add the square and the circle to the group, create it, then show an animated shift right, and that will move everything in the group to the right. So draw, shift. So hopefully this is giving you an idea like how to build up more and more complicated things. So I think this is like the last demo of simple shapes. Here are some more things you can do. Rectangles. So this is a rectangle of width 2, height 4. Here's one of width 4, height 2, with internal subdivisions, a grid inside the rectangle. Then here's an arrow with a start and end position. And I'm looking to see that center of the grid and the top of the rectangle to get the coordinates of the arrow. And then I'm creating a group, adding everything to the group, and then showing an animation, creating the group that will take 4 seconds rather than the 1 second by default. So a slightly slower runtime. And then we'll just wait at the end. So you can see the rectangle, the grid rectangle, and the arrow. All right. So at this point, we have enough tools to start doing something interesting. And so the first real example is going to be CS. So I thought about doing differential equations, and like everyone vetoed that idea. So no differential equations. We're going to do a linked list. So this is a representation of a linked list that uses boxes and arrows. And we're using this grid thing to do a box that has a division inside the box. So it has like a contents and a pointer inside the rectangle. So we're going to have two nodes, move the second node to the right of the first node, have an arrow between them, make a third node, move it next to that second node to the right, add another arrow from 2 to 3, then group everything together with all these nodes and the two arrows, and then shift things left to keep them so because like everything starts at the origin and we were going to the right, so let's sort of shift it to the center a bit, and then show the animation drawing. This is a representation of a linked list. It's not super exciting yet, though, because it's just drawing it. So maybe we want to illustrate some operation like removing an element from a linked list. So here we're trying to say we're going to remove that middle element and change that first arrow to point to the third element because we removed the middle one. So there's the same setup code. We draw the original linked list. Now we're going to fade out node 2 an arrow from 2 to 3. That's the middle one and the arrow. And we're going to create a new arrow that goes from 1 to 3. And now we're going to transform, which is a new kind of animation, arrow 1, 2 into arrow 1, 3. So the arrow that pointed from node 1 to node 2, we're going to morph it into an arrow that points from 1 to 3. So that's the same. That's the fade out. And that's morphing the arrow. And now it's illustrating this like removing an element from a linked list for your computer science lecture. Except it's not quite done. So here's a slightly better version. And so now we're adding a little bit of color, a little bit more bells and whistles. And so here we're making the arrows have a color yellow. We're adding some text that's blue, that's labeling the different nodes. And so we're saying these blue texts are going to be next to the nodes on top, to like be labels on top. And then we're adding a dot with a radius as sort of like the end of the linked list, a null pointer to say this is the end of the linked list. And then we're putting all that in the group, and then we're doing that same transformation as before. Now we have colors and labels, and it looks even nicer. All right, next computer science example, binary tree. So here's the one-page example of binary tree. So BT is a function that returns a group that is the binary tree, and you give it the value at the root and a left and a right, which are binary trees. And so this first part here, we create a node that's a circle, and it has some text, which is the value. So if we give it like 5, it'll be a 5 in a circle. That's kind of our node of the binary tree. And now left and right, we have this problem where binary trees have to like end at some point. So we have none to say there is no child if there's a left or a right that has a none. So we have to have a way to sort of end. And here, if it's not none, then we just keep the left or the right that we're given. If it is none, we create a smaller black transparent object circle, just so it takes up space, so our tree won't be vertical, and we can tell which side children are on, if that makes sense. Then we move the right next to the left, so the right child has to be to the right of the left child. We align their tops. We group the children together. We move the children down from the root, so we align the children right below the root. We group those together, and then if the left and the right are not none, we add arrows from the root to the child. But we don't add the arrow if they're none, because then we just have the black placeholder object. Here's how we use it. So here's a binary tree that has 7 at the root, then a binary tree with just 5 on the left side, and a binary tree with 10, and then 8, 11 branching down. And move it to the center, show the animation for drawing it, and then just wait. So that's what it looks like. It's not perfect, but it shows what's going on. And once you have the function for creating the binary tree graphics, right, this one line here, I can change that one line of code to do lots of different examples, right? So this is kind of program idea where you program it, then you just do it lots of times easily. So here is an example of doing that. We have tree 1 and tree 2, which are slightly different binary trees, sort of rebalancing the tree. And we do an animation where we create the first tree, then wait, and then we fade transform, which is like fading out the first one, fading in the second one to show the rebalancing of the tree. There's the first one, fades to the second one. And you might think, why not just use regular transform? And the answer is, the nodes don't actually move correctly if you just do a transform. So like the 7 doesn't move to the new position of the 7. It just morphs the 7 from a 5 to a 7 or whatever it was. Yes, you can say, yeah, for all these transforms and different animation constructors, they have an argument runtime, and it defaults to 1 second. But you can say 5 or 10 or whatever you want. All right, so now the final binary tree one is showing an insertion into a binary tree. So trying to do an animation that's like kind of actually correct, showing what's going on in a binary tree. So the idea here is construct the binary tree and show it. Construct the new node with a new color, so it'll be blue instead of whatever the original one was. Then we're going to move that new node that we're inserting to be above tree 1, 0. So remember, tree 1 is that group. So this is showing indexing into the group to get different parts of it. Right? That original group, the first part was the root node of that tree. And so this 0 will be the root of the entire tree. Then we're moving, you can see this node animate next to, we're moving that node next to different parts of the tree. So 1, this is the child part of the original root. 0 is the left side, left child. Then here, this is the child part, left side, child part, left side, so like the left node. And we're just moving that insert node down the tree. And then finally, it needs to go somewhere new that's not actually in the tree, and so we sort of shift it to sort of be where it could be. I sort of made some numbers there. And then we have our updated tree, and so we do that transform from tree 1 to tree 2. So here's what that looks like. The original tree, the new node to insert, it's going down left, and now it's going to sort of where it should be. And then there's our new tree. It's doing the transform, showing the drawing. Any questions about this so far? So there are some libraries, I would say, so I looked for good libraries and I found many examples. So I would say there are no high quality libraries for doing all this basic stuff in a consistent way that you can just use directly. It's mostly examples. So you have examples of lectures that do binary trees, and they have a whole bunch of code for doing binary trees, and you can use their code to get the same look that they have. But it's a little bit hard because different people have different ideas about the layout of binary trees, and the nodes might be bigger or smaller in some examples, and like here they're kind of round, uniform size. So there are some assumptions that every person makes, and it's mostly examples, not a reusable library, I would say. All right. So now we're at the point where I can start talking about the slides I did for my talk at Code Camp. And this is doing functional block diagrams for deep learning networks. So here's some code. So I'm not going to explain all the code here. I just wanted to show an activation is a function or is a class I'm defining, which is a V group. So it descends from V group, and it has a new constructor. And in the end, it creates a bunch of things and then calls the super, which is the V group regular constructor, to put these things into the V group and then returns itself like as a V group. It's a specialization of V group. And so you can create an activation and call it with these parameters, and it will act just like a V group, but it will have the right look. That's kind of the idea here. And what's it actually doing? So an activation is a rectangle filled with a nice, smooth, curvy function. That's this cubic Bezier curve. And then there's... So it does not require NumPy arrays. I was using NumPy, and so that's what I was familiar with. Yeah, I tried to use regular arrays, and I had some problems, so I used NumPy arrays. I don't think it technically requires NumPy arrays. Yeah, then there's a thin line that's showing the center line of this curvy Bezier curve. And then I'm also recording the inputs and outputs of this block, because this is part of a diagram where it can have multiple inputs and outputs. And I'm going to be hooking all these little blocks together to make, networks of blocks. And so I'm recording that in the object. So here's the example of using it. Construct one with default arguments, another one where you change tan h to be true, which changes the little reference line. And then we move that second one below the first one. And we group them together and draw them. That's kind of what it looks like. All right, so here's the first one. This is a sigmoid. The reference line is on the bottom, and the second one is a tan h. Reference line is in the middle. They're just blocks for a block diagram. And now that we have activation defined, we can start specializing more and more. So here's a linear activation, which includes an activation plus a whole bunch of other stuff. And I guess one thing to mention here is that I'm adding some tech. So text takes a string and just draws it. Tech actually takes a string of LaTeX math commands for doing math rendering and then renders that math equation. And that means you can do subscripts and powers and all kinds of stuff inside the annotation, which is very handy. These little lines here, this line stuff, are like the inputs and outputs. They're showing little lines that'll be connected together to sort of show the inputs and outputs. And this is just going over the range of inputs to put little ticks at the right places. And then there's separate methods here of get inputs and get outputs. So making it not just a data field in the class, but actually a method that computes some stuff. And then to use that linear activation, here's a little scene. So it creates a linear activation, then I create X and Y labels using tech. And so this will create X and Y with the right font, the right look, and put that on the top and the bottom of the linear activation. And then we'll show that. So you can see the X and the Y are the labels, and then this whole thing in here is the linear activation. It's this function thing, the activation, and then this box that represents a matrix with the right dimensions. That's kind of what's going on. And we can go another level up and start using multiple linear activations, right? So that's the trick here, is we do these simple things and just keep building it up and create more and more classes, more and more functions, get more and more complexity. So an MLP is a multi-level perceptron, which is multiple linear activations stacked on top of each other. So here we have linear activation, X, linear activation, another linear activation, then put them all together, and then output y at the bottom. So there you go. So we have our stack of linear activations, and this is representing a network where you have the inputs at the top going through these matrices, through these functions, and like these dimensions are all matching up, and we're getting our output. That's kind of the idea here. And then for the final level of complexity, GRU has multiple linear activations inside of it. And so at the GRU level, this is a very big network. And so what I did is I used Python as the data store here. And so positions are where everything is in XY coordinates. Then contents is what is in that position. And then the edges are what is being connected by lines. Right, so I sort of wrote this out by hand with lots of iteration. And then there's a little for loop here, drawing the things at the right positions. Right, so drawing these contents and shifting them to the right position. And then for every edge, getting the inputs and outputs, like getting where those edges connect, and drawing a line from the input to the output, or the output to the input, sorry. And then to use the scene, you just construct a GRU and then create it. So this is the GRU, the gated recurrent unit. And you can see like each of these is a linear activation. Up here, these were these op boxes, and there's like things connecting. There are these special dot splitters for keeping the lines going nice ways. So significant complexity, but then again, you can keep going. This has 2 inputs and an output. You can start stacking these and make more layers, and that's kind of the game in this deep learning stuff, is having more and more layers, making things more and more complicated. So if you want more examples, there are many, many more examples on the Manim community pages. And in fact, the documentation has a whole series of examples here. It includes things like 3D, which we didn't get to at all, which I think is, extra complicated, so a little bit beyond me. But you can do 3D. There's lots of examples of other mathematical things like functions and tangents to functions, things like that. I kind of tried to keep it on the CS side for this talk. So my final thoughts here. Manim does have some limitations. I think it's not great for video composition. So if you're trying to do a final YouTube video and you have a video camera and you want to like have yourself talking, like a talking head, and then you cut to the Manim animation, and then you cut back, and then maybe your talking head is in the corner while things are animating. Manim can't do that directly, right? So Manim generates the math animation, and you probably will need some other video tool to do the normal talking head video, and then dissolve to the animation, the math animation, go back and forth, stuff like that. Timing of voiceovers is really tedious. So if you're doing some example and you'd like to do a voiceover that talks about what's happening at the right time, it takes some experimentation. And there are some tools that can help you, but the way I do it is I do the voiceover part first. Like I have an idea of what I want it to look like, and I record the voice. Then from the voice, I add delays to the code to make it fit. And I try and do like 10 seconds or less each time. Yep. Yeah, if you want to have a pause where there's a lot of speaking, you can, that's exactly what you do. Yeah, you manipulate the animation video, you can chop it up, you can take a paused frame and spread it and then just duplicate that static frame so you can talk as long as you want while it's waiting. So another limitation is that when you're writing Manim code, it's kind of stateful and imperative. Like you're telling it, do this, then this thing moves here, then this object changes this way. And what that means at every point in time depends on everything that's happened previously. That's sort of the imperative style. There's a state, you're manipulating the state, different operations happen, the state keeps getting updated. that can be sort of brittle. So for example, if you comment out one line in your Manim file, you might totally break everything in your animation. Because the, move this next to this, now move everything down, and now scale everything back by a half. If you comment out the scale everything back, everything following that could be totally wrong. And so that's kind of annoying. I personally don't like this aspect of the Manim interface. It makes it harder to copy and paste code and reuse code because of the sort of statefulness of the interface. Another problem is interactivity. So there are ways to do interactive Manim videos where you're generating the video on the fly as the user's doing things, but it's not the strong point of Manim. It's not, I actually wouldn't recommend doing interactive Manim. I'd recommend pre-rendering a bunch of videos and choosing between them. So if there's like one slider and you have 10 different videos, you choose which of the 10 videos. That works well. Trying to do like JavaScript style, it doesn't really work in my experience. So when should you use Manim? If you're doing technical diagrams, I think it's actually a good choice. I like it better than using Inkscape or Adobe products and things. And mostly because of version control and sort of the programmability, being able to do things in functions and classes and not having to redo the same thing over and over again. It's really good for animated state changes, showing what's going on. It's really good for standalone animations, like for doing slides and videos on YouTube and places. Another great point is you can use the whole Python ecosystem for doing your data and your computation and anything you want. And that's a huge plus because you can show your actual data that you're demonstrating, or for example, you can generate thousands of examples and pick the best ones for binary trees. And if you need to, generate another 1,000. It's not a problem. Here's some links. So the main one is manim.community. There's also reference manual, examples. There's also a awesome directory. So that has a showcase of YouTube videos and other cool things people have made using Manim. And that's pretty fun to watch. So here's an example. And this is connecting back to BSDG. So Advent of Code for last year, which was a talk I don't forget when it was, but there was a talk about Advent of Code. And day 16, there's a question about paths and finding the minimal shortest path on a grid. And so here is Dan for Life making a YouTube video, which is a Manim animation of day 16. Yay, it found it. Now it's checking if it's minimal or not. Here's a different example. You can do it. Yay. And so you can imagine writing the code to do that algorithm is a certain amount of work. Writing the animation code in Manim for that specific algorithm is another amount of work, but it's not that much. It's not a lot more work, right? It's on the same order of magnitude as doing the original algorithm. And so if you want to present the work you're doing, adding animations like this is a very powerful way of showing what's happening. All right, that's the end. And before I say bye, I wanted to say I'm doing a meetup at Bound Library on August 6th. Code is art. So this is a creative coding meetup thing. And the idea is I'm going to give an intro to the artist and then do a demo of the artist's work and then show some of the code that's making the art. And this is an example. This is Danielle Navarro generated artwork. So if you're interested in programmatically generated art. Please stop by. So August 6th at Bound Library, 6 p.m. All right, that's it for me.
What are the options? Is there something better? Maybe easier to use, or I don't know, harder to use, but with some other user?
Yeah, I see. I think for yeah.
Your last demo with lots of boxes connected with lines. Can it be then the line be geometry of lines be generated automatically, like in some graphic packages, where you just define the graph and it tries to find out a nice graphical planar representation of it, or you have to all of those lines over there, including the dots, connecting them, you have to specify manually, right?
Yeah, so I did it manually or semi-manually, like the blocks. I did it block by block. So each block has the code that sort of figures out where the inputs and outputs should be, and then I put the blocks in manual places, and then sometimes the lines would cross. Like, let me go back here.
Also, some of it was generated automatically.
Let me see. Yeah. So like, for example, choosing where to put this and this and this, that was done manually. I just picked where. Then originally I had it be like the x of t would go to this input, so it would draw this line. Then this output would go to this input in a straight line. And then that got a bit jumbled. Like there's no great way to do the graphs without any lines crossing. And so I added these splitters and kind of did it manually. There are packages. Yeah. 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 And so there are tools for doing graph layout that can do this kind of thing. I looked at those briefly. They seem pretty advanced, and they don't always work too. Like there's lots of different criteria, like what is good. So having one line that crosses might be terrible for one person and fine for another application. So like the way they score the graphs is kind of complicated. For me, I was fine like flipping the H and the X at the top. I flipped those to make space and it worked fine. Like whether you allow that sort of stuff makes it complicated. But there are libraries for doing graph layout, but I decided not to use them. At a higher level, there are lots of ways of describing networks like this that are not Python code. Like you can use a graphics program or a vector drawing program or diagramming software, and that can be effective. The problem with those for me is that I wanted to have this sort of technical stuff inside, and I wanted to be able to show exactly what's happening and also move it around the screen and change things. So like if I'm using a generic vector graphics program, that becomes harder if I want to animate things. Did you have some diagram software?
Yeah, next month I was going to do software architecture as code using C4. So happy to do it. It's similar field. So I'm trying not to stack two talks back to back that are pretty similar, but I've also had no other submissions. So going to software architecture diagrams as code. Again, that's very much a node edge type thing. So here's a node. There's an edge between them. It's using things like GraphViz under the hood, which most diagrammers code tools use under the hood to do that. But it's not necessarily going to give you the kind of capability and power that like a full animation engine would give you. So again, kind of different tools for different problem sets, right? And I imagine, being that we're all software developers, we could probably find novel ways to tie the three together if we really wanted to.
Yeah.
So how long does it take to render like that 7-second video?
Let's see. What's this one called? This is called GRU Scene. I haven't tried this, so that means it's going to crash, right? This is quality level P. Oh, what? Quit. Oh, it's not in examples. It's in... What is it? don't have it here. Maybe I'll have to do MLP. There it goes. So it's not super fast. This is the MLP video. I don't remember how many seconds it was. Yeah, so P is the very high quality. So this was a 5-second video, I think. So it, like, it's fast enough to do that at low quality. Yeah, so that was the P quality, and then I can show you the L quality for the same one. Right. It's faster than real time, so faster than 4 seconds. Yeah. So in the community edition currently, the fundamental engine is like vector graphics in Python that are rendered to PNG files that are created, they're like grouped together by FFmpeg into a video. The old version, like the original Manim fork, had pure Python stuff originally, then it went to an OpenGL rendering system, but then that got complicated and kind of was deprecated for the community edition. And the community edition uses like Cairo and stuff within Python to do the actual PNG render. So yeah, I think the main competition for Manim in my mind is really like JavaScript graphics libraries, like the sort of game programming graphics libraries. So they have interactivity, they have, you know, squares and circles and things, they can draw quickly. And then if you want to do something fancy with mathematics, JavaScript actually does have a pretty deep system, like a deep ecosystem of math libraries and things you can do. What it doesn't have as much is the data side. So if you want to grab a data set and extract a column and normalize the column, all that stuff, like JavaScript might be possible to do that, but Python is like, the whole scientific ecosystem is in Python pretty much for doing all that stuff. All right, any last questions?